All right, welcome to Waves of Light Part 2. In this video, I'm going to talk about the relationship between frequency, which is the symbol nu, lambda, which represents wavelength, and we're also going to talk about energy. So the speed of any wave, which is represented by c, is equal to the wavelength multiplied by the frequency. Now, for the type of waves we're interested in looking at in chemistry, electromagnetic waves, remember, electromagnetic waves do not require a medium to travel through. The speed of all electromagnetic waves will be approximated to be 3.00 times 10 to the 8th meters per second, which is the speed of light. So in the previous lesson, we saw that frequency is inversely proportional to wavelength. That is, as the wavelength gets smaller, the frequency gets higher. So when we take that relationship and apply it to our speed of wave equation, we get frequency is equal to the speed of the wave divided by the wavelength. And for our purposes, again, the speed is going to be equal to 3.00 times 10 to the 8th meters per second, since we're going to be dealing exclusively with electromagnetic radiation. So what can we do with this equation? Well, we know that in the visible region, 700 nanometers is equal to red light. So let's say I wanted to find out what the frequency of red light is. All right, so frequency is equal to the speed of light, 10 to the 8th meters per second, divided by 700 nanometers. Now, this is the common mistake that I see with my students calculating the frequency. If we take what we have here, the meters does not divide with the nanometers, or the nanometers does not divide with the meters. And we know frequency should be a number over seconds, which represents waves per second or cycles per second. So in order to solve this problem, we are going to have to convert the nanometers and 700 nanometers to meters. And the easy way to do that is, again, we'll write the speed of light now. And then we'll write 700, but nano means 10 to the negative 9th. So I'm going to say 700 times 10 to the negative 9th meters. So nano means 10 to the negative 9th. So when we have a nanometer, that's 10 to the negative 9th meters. Now, watch what happens. The meters here become unity with the meters in the denominator. We're left with the number over seconds. So if you get your calculator, we would say 3 exponential 8 divided by 700 exponential negative 9. We would hit equals, and we would get for an answer 4.285 7 times 10 to the 14th over seconds. That's the only unit that's left here. Now, some of you may be going, well, that's a lot of digits. So if we were going to talk about significant figures, how many significant figures should we have? Well, 3.00 has 3. 700 actually has 1. If you want to make it 3, you should put a decimal after the 0 here. All right? So I'm going to make it 3. I'm going to cheat and make this 3 so that we get 3 significant figures in our final answer. So we go 1, 2, 3. We do look at the 5 here. If the number is 5 or greater, we round up. So my final answer would be 4.29 times 10 to the 14th over seconds. Or if you want to clean it up some more, it would be 4.29 times 10 to the 14th, and you could say Hz, hertz. All right. Let's continue on. In the next example, I want to show the relationship between energy and wavelength and frequency. Energy, according to Planck, energy was equal to N, which always was a whole number, times Planck's constant, times the frequency. Now, we generally simplify this as just E equals Planck's constant times the frequency. We don't look at the multiples of N. This equation can be further enhanced by saying energy equals Planck's constant times the speed of light divided by the wavelength. These are all equivalent. If you know the wavelength, you'll use this equation. If you know the frequency, you'll use this equation. Now, the equation illustrates this, that there's a direct relationship between frequency and energy. The higher the frequency of the electromagnetic wave, the higher the energy, or the greater amount of energy in that wave. This equation, the shorter the wavelength, the higher the energy. So we saw in the electromagnetic spectrum that the shortest wavelengths were gamma rays. Gamma rays would have the largest amount of energy. The longest wavelengths were radio waves, and they have the lowest amount of energy. So how do we use this equation? Well, let's focus on our 700 nanometers again. 700 nanometer radiation is equal to the red light in the visible spectrum. And we determined the frequency from our previous problem to be 4.285 or 2857 times 10 to the 14th. Now some of you are saying, well, we didn't need all these significant figures. Well, if we're continuing on with the calculation, you want a lot of digits. You want a lot of significant figures. Because if we take the 4.29 that we got from our previous problem, at that point we've rounded the number off, and every time we would do a calculation, if we round it off, in the end we'll get round off error. So if we're going to continue on with our calculation from the previous page, we want more than just 3 significant figures. Then we'll round off at the end. So right now we know that our least significant figure lies on the 8 here. Alright, so we'll keep that in mind. Alright, so if we want to know what the energy of red light is, we'd say energy equals Planck's constant, and Planck's constant is 6.636 times 10 to the negative 34 joule seconds. Joule's an energy unit that we use. And then seconds, we know what a second is, all right? So if we multiply this by 4.2857 times 10 to the 14th over seconds, the frequency, the seconds will cancel out, and we will be left with joules. So let's take our answer, 4.2857 times 10 to the 14th, the frequency of red light, multiplied by 6.636 exponential negative 34 joule seconds, and we get 2.844 times 10 to the negative 19th joules. That is how much energy is present in one photon. Now, what's a photon? Well, a photon is a packet of light. So we think of light sometimes as packets, and we call those photons. And this is the amount of energy in one photon. Now, before I would report this answer as my final answer, I would round it off to the correct number of significant figures. We know that this frequency only had 3 significant figures, so we should report our final answer. This is a constant, and it's known to 4 significant figures, or that's the way I've written that one. So I would report my final answer to 3 significant figures. So it would be 2.84 times 10 to the negative 19th joules. And if you want to say joules per photon, that is fine. That's how much energy is in one photon of light in the red region of the visible spectrum. I hope this helps. And if you have other questions, please contact me. Thank you.